Good evening, sir.
Yeah, hi, good evening.
Hello, good evening, sir.
Yeah, hi, good evening. Oh, okay. My microphone was muted, so hi, good evening, all. Can you hear me properly now?
Yes, sir.
Yes, sir. Yeah. Okay, so let's wait for others to join, then we'll start. Okay, just a second. So the UPS alarm is warning actually. Okay, so any doubts on last three questions? Okay, great. Okay, so now we can start. Okay, thanks. Okay, so today also we'll be solving three physical chemistry questions from 2018 paper. And okay, so first, okay, so let me just share my screen and then we can start. Oh, why it is showing error? Just a second. Okay, so let me just join again. I think there is a problem. Actually, is my screen visible now?
Yes, sir.
the tablet screen?
Yes, sir.
Okay, thanks. Okay, so let's start. So this is question number 10 from 2018 paper, and the question says, for ionic micellally forming surfactant near its critical micelle concentration, which is CMC, the dependence of molar conductivity and the surface tension on the surfactant concentration is the best represented by which of the following four figures?
So slide is not visible to me.
Okay. Why it is happening? Okay, just a second. This will not happen. Oh God. Okay, now it is visible, right?
Yes, okay, sir.
Yeah. I don't know why this problem is happening again and again. Okay, so let's start. So this is question number 10 from 2018 chemistry paper, and the question says, for an ionic micelle forming surfactant near its critical micelle concentration, which is CMC, the dependence of molar conductivity and surface tension on the surface concentration is best represented by which of the following four figures? So Okay, so in this question it is the surfactant is ionic, so it is ionic surfactant. That means it can have hydrophilic head group, hydrophilic head group. It can be cation or anion, it can be, and hydrophobic tail group. So surfactant is basically a long chain hydrocarbon with a tail group which is hydrophobic in nature, and with a head group which is hydrophilic in nature. And the hydrophilic group can also have a cation or an anion. So let's first deal with the molar conductivity. Like what will happen in the molar conductivity? We change the surfactant concentration. Okay, so basically this is the pictorial representation. Like this is a water solution, and then these the long chain hydrocarbons are surfactant molecules with a hydrophilic tail group. This is actually tail group. So first, when we add surfactant molecules in the solution, the surfactant molecules will deposit on the surface of the solution. Why? Because the surfactant molecules are called surface active agents. So when we first add little amount of surfactant molecules in the water molecules in the water solution, then the surfactant molecules will first deposit on the surface with the tail group, which is hydrophilic in nature. So that's why the tail group is interacting directly with the water molecules, and hydrophobic group, which is the tail group, actually trying to avoid the water molecules because they are hydrophobic in nature. So they first deposit on the surface. Then if we again keep on adding the surfactant molecules, then the surfactant molecules will keep on depositing on the surface of our system, or of the water molecules. So at a particular concentration, when all the surfactant molecules are actually deposited on the surface, or actually covered the surface of our system whole completely, then after that, if we all keep on adding the surfactant molecules, then the surfactant molecules will starts to form micelle. Now this is the micelle looks like all the hydrophilic tail groups, because they are hydrophilic in nature, so they want to interact with the water molecules, so they are just outside of the micelle. These hydrophilic tail group, hydrophilic head group. So these head group are hydrophilic in nature, means they want to actually interact with the water molecules. So these are water molecules outside. So and the hydrophobic tail group, which are trying to avoid the water molecules, so they just form a micelle type formation, like cage type formation, and trying to avoid the water interacting with the water molecules. So these are called micelle. So what is happening, first we add little amount of surfactant molecules, then the surfactant molecules will be deposited on the surface of our system. Then if we also keep on adding the surfactant molecules, then surfactant molecules will completely cover the surface of our system. Then after that, at a particular concentration, the surfactant molecules starts to form micelle type structure. Now let's deal with the molar conductivity. What will happen the molar conductivity if we change the concentration of the surfactant molecules? So basically molar conductivity is denoted with the sign lambda, capital lambda. It is the lambda equal to kappa divided by C, which is the kappa is the conductivity, kappa is the conductivity of electrolytic solution, and the C is the concentration of the solution in mole per liter. So basically it is the concentration of the solution. So we know that if we decrease the concentration of our solution, the molar conductivity will decrease. From this equation you can clearly see, if we decrease the molar concentration of the electrolytic solution, the molar conductivity increases. Molar conductivity, molar conductivity increases. If we decrease the concentration of a solution, the molar conductivity increases. Now there is a relationship between this concentration of the electrolytic solution and the molar conductivity. So we know this relation is actually Cole-Ra's law, or we can actually call it the Debye-Huckel-Onsager relationship, which is Debye-Huckel-Onsager relationship, or law, which says the molar conductivity of an infinite solution, which is denoted by capital lambda, equal to lambda 0 or lambda naught, which is the molar conductivity of the same electrolytic solution at infinite dilute concentration, minus capital K root over of C. So here capital K is the Cole-Ra's constant, KOHLUCH, Cole-Ra's constant, and here C is the molar concentration, lambda 0 is the molar conductivity of the same electrolytic solution at infinite dilute concentration. Infinite dilute means very dilute, and this is the molar conductivity of the same electrolytic solution at concentration C. So this according to this relationship, if we draw a plot of molar conductivity times against the root over of concentration, so we will get a linear relationship, and the molar conductivity decreases with the increase of concentration. So if we apply this equation or this concept to this question, so if we first we are adding the surfactant molecules, little amount of surfactant molecules in our solution. So the molar with the increase of the concentration of the surfactant molecules, the molar conductivity will decrease first according to this relation. So let's say this is the concentration of the surfactant molecules, and this is, let's say, molar conductivity. So with the increase of the concentration of the surfactant molecules, so molar conductivity will decrease first, but here the molar conductivity will decrease very slowly. Then at a particular concentration, let's say, which is the critical micelle concentration, so at this concentration all the surfactant molecules are completely covered the surface of our system. So and after this concentration, if we start increasing the concentration of the if we start adding the surfactant molecules starts to form the micelle type structure. So let's say it is the CMC. Now what will happen after CMC or critical micelle concentration, the surfactant molecules start to form micelle type structure. So that means this type of structure. So what will happen, so there is a so these are ionic surfactant, right? So that means, let's say the head group is positively charged here. So if we consider one mycelium type structure, so there is a net positive charge of the mycelium. So let's say for this type of mycelium 1 2 3 4 5, so the center of the mycelium is positively charged. Sorry, this is wrong structure. This is hydrophilic tail group, head group, and this is hydrophobic tail group. So these are, let's say, positively charged. So if we consider this type of mycelium structure, so for one structure there is a net positive charge which is 1 2 3 4 5 6. Let's say this is +6. So the whole mycelium structure contains +6 positive charge, and there will be counter anions to neutralize this charge. So there will be 6 negatively charged ions or anions, negatively charged anions. So the total charged species here is 6 plus 1 mycelium type structure, which is 7. Now before forming the mycelium type structure, what will be the amount of charged species? So 1 2 3 4 5 6 surfactant molecules with positively charged plus 6 negatively charged counter anions. So there will be total 12 charged species. But after forming mycelium type structure, the total number of charged species decreases to 7, from 12 to 7. So that means after CMC the number of charged species decreases, so due to formation of the mycelium cage type structure. So number of charged species decreases means molar conductivity decreases means molar conductivity also decreases. So that means after CMC the molar conductivity starts to decrease gradually. So the trend of molar conductivity should look like this. First it will decrease little bit amount, then after CMC, due to the formation of mycelium shape structure, the total number of charged species decreases. So that's why the molar conductivity decreases. So the trend of molar conductivity with surfactant concentration looks like the B plot, option B here. Now let's deal with the surface tension. What will happen in the surface tension? So surface tension, so surface tension is basically surface tension is a property that is when the liquid liquid molecules on the surface actually tends to shrink to a shape of minimum surface area. So the surface molecules actually tends to shrink to a shape of minimum surface area. Why? This surface tension generates due to the difference in intermolecular interaction. Difference in intermolecular interaction. Yeah, I think it is on. Difference in intermolecular interaction. Why? Because let's say this is a beaker containing water molecules. So this is bulk system, and there are water molecules on the surface here. So we know that water molecules, there is a strong intermolecular hydrogen bonding between the water molecules like this. This hydrogen generally form a strong hydrogen bond with neighboring oxygen atom. So this is a strong hydrogen bond. Now let's say there are water molecules on the surface, and there are water molecules also in the bulk. Now in the bulk, what will look like in the bulk, let's say there is one water molecule, and again there is other water molecules surrounding these water molecules. So this center water molecule generally form strong hydrogen bond with other water molecules, but in the surface, let's say this is surface and there is a water molecule here like this, there is a water molecule here like this. So this OH bond or this hydrogen atom actually can form strong hydrogen bond with another water molecule, another neighboring water molecule. But this OH bond or this hydrogen and this hydrogen atom which cannot form hydrogen bond with water molecules, right? Because this is the surface and this OH bond actually above the surface, so it cannot find any other water molecule surrounding it, so that's why it cannot form hydrogen bond with other water molecules. So the hydrogen bonding interaction between the water molecules is stronger or is much larger in the bulk system. Why? Because all the hydrogen atoms or the oxygen atoms can form hydrogen bond with other water molecules, but the hydrogen bonding interaction between the water molecules at the surface is much less. Why? Because all the hydrogen atoms or all the atoms cannot find surrounding water molecules there. So there is, we can see there is a change of intermolecular interaction. Like in intermolecular interaction is stronger in the bulk compared to in the surface. So that's why all the water molecules in the surface tend to go or want to go in the bulk phase, where they can form strong hydrogen bonding. So all the water molecules, that's why all the water molecules in the surface can actually feel a tension to go to the bulk phase. So that's why the surface tension generates. So this is the concept, behind the scene of surface tension, you can call it. Now what will happen if we add the surfactant molecules? So previously I have said that the surfactant molecules are surface active agents, right? That means if we add surfactant molecules in the water system or in the liquid water, then the surfactant molecules actually tend to occupy the surface of the system. That means if we add surfactant molecules, it will deposit on the surface. So it will deposit on the surface means the previously there were water molecules here, right, at the place of surfactant molecules. So surfactant molecules come and replaces the water molecule on the surface and deposit on the surface. So now water molecules actually, so the previous water molecule which were occupied on the surface can come to the bulk phase here. So first let's say this is surface, there were water molecules here. Now if we add two surfactant molecule, so they can actually come and deposit on the surface and by replacing these two water molecules. So now what will be the picture? These are surfactant molecules. Now these two water molecules can come to the bulk phase. Now they can form much stronger hydrogen bond in the bulk phase, right? So due to the properties of surface, property of surface activity of the surfactant molecules, the water molecules can now come to the bulk phase and form stronger hydrogen bonding. So the surface tension decreases in this case, because the water molecule now are now in the bulk phase, so they can form strong hydrogen bonding. So that's why the surface tension decreases upon adding the surfactant molecules. So first, if we add the surfactant molecules, the surface tension will decrease, like option B. Now at CMC, at critical mycelic concentration, the surfactant molecules, all the surfactant molecules are completely deposited on the surface here. Now after that, if we keep on adding the surfactant molecule will starts to form mycelium type caging structure. So since all the complete surface is now covered by the surfactant molecules, there were no water molecules in the surface, so that's why the surface tension actually don't decrease much here. So they actually like achieve a saturated value of surface tension. So that's why after CMC or after critical mycelium concentration, the surface tension actually do not decrease much, so they actually achieve a saturation value of surface tension. So this will look
So-
like, yeah.
Please repeat last 3 lines.
Okay, so before CMC it was right. Okay,
Before CMC, okay.
Yeah.
After CMC.
so after CMC what will happen, after CMC all like at CMC all the surfactant molecules will be completely covered the surface, right? So after CMC, if we keep on adding the surfactant molecules, so it will starts to form like mycelium type structure. So after CMC all the complete surface is now covered with the surfactant molecules, right? There were no water molecules in the surface, so that's why the surface tension of water decreases now, because there were no water molecules on the surface. There are no water molecules on the surface means the water molecules on the surface, water molecules cannot actually feel the tension to go to the bulk phase and form stronger hydrogen bond, right? Like all the water molecules now are in the bulk phase, so that's why there were no tension here. So that's why the surface tension decreases, then after CMC the surface tension don't decrease much, so it actually achieves a saturated value. Is it
Okay, sir.
Is it okay? So the correct option is option B. The molar conductivity first decrease little bit by little bit. If we increase the surface concentration, then after CMC, due to the formation of mycelium type structure, the total number of charged species decreases. That's why the conductivity decreases and molar conductivity also decreases. And the surface tension, if we first keep on adding the surfactant molecules are will be deposited on the surface by replacing water molecules, so that's why the surface tension first decreases. Then after CMC all the surfactant molecules are completely covered the surface, so the water there are no water molecules on the surface to feel the tension or to go to the bulk phase and form stronger hydrogen bond. So that's why the surface tension value actually attains a saturated value. Okay, so the option B here is the correct answer. Okay, so is it okay?
Yes, sir.
Yeah. Okay, now we can okay, now so let's move to the next question, which is question number 34. To get used to it. Okay, so this is question 34 from 2018 paper, and so this is a question about the perturbation theory in quantum mechanics. Like the question says a one-dimensional anharmonic oscillator, which anharmonic means which is not harmonic oscillator. So a one-dimensional anharmonic oscillator is treated by perturbation theory. The harmonic oscillator is used as the unperturbed system, and the perturbation is 1/6 gamma x cube, where gamma is a constant. Using only the first order correction, the total ground state energy of the anharmonic oscillator is. So here the one-dimensional harmonic oscillator ground eigenfunction is given, the wave function is given. Now we have to find out the total ground state energy of the anharmonic oscillator. Okay, so let's start some basics of the perturbation theory. So perturbation, why we use the perturbation theory? Because for some system, let's say now in this case anharmonic system, anharmonic oscillator, so we cannot solve this type of problem explicitly, like for harmonic oscillator or hydrogen atom problem or free particle problem. We can solve this type of problem quantum mechanically explicitly, but for other systems or other problems we cannot solve the quantum mechanical problem explicitly, like exactly. There are no exact solution of some kind of problems. So that's why we have to approximate the solution. Now how can we approximate this solution? So like there is one approximation method is perturbation theory. There are also other approximation methods like variation principle, etc. So in perturbation theory, so let's say we have a Hamiltonian upward system, unsolved system which cannot be solved exactly. This is the Hamiltonian operator. Now first we approximate this Hamiltonian with a unperturbed Hamiltonian of an unperturbed system, which is H0 plus lambda times a perturbed part. Let's say we call it V. So H0 is the Hamiltonian for the unperturbed system. Unperturbed system means we solve this quantum mechanical system exactly. Now we are adding the perturbation term here, where lambda is the perturbation. So perturbation, and then we call it lambda is very small. So the perturbation theory will work for weak perturbation, for weak or small perturbation, and V is the perturbed term. So first we approximate H equal to H0 plus lambda times V. Now we know the exact solution of H0, but we don't know the exact don't know the solution of H. So that's why we are approximating this H with a H0 plus lambda times a perturbed term V. These are all operators. So let's say first the eigenfunctions or the eigenvalues corresponding to H0 satisfy this equation. H0 plus N0 equal to, let's say this is eigenvalue En0 times N0. So H0 is the Hamiltonian operator corresponding to the unperturbed system. N0, this is the eigenfunction of the unperturbed system. Nth eigenfunction, this is the 0th order eigenvalue for the unperturbed system, and this is the eigenfunction. So we know this relationship exactly because we can solve the quantum mechanical problem of H0 unperturbed system exactly. Now we don't know this problem, like N equal to En times N. So this is the time independent Schrodinger equation for the total system, total Hamiltonian. like h. We don't know this solution of this equation. Now using perturbation theory we will solve this equation. So first we know this relationship. Now we will expand the eigenvalue equation En, this equation, with different orders of lambda, like En equal to first term will be 0th order term, like for eigenvalue, nth eigenvalue corresponding to the unperturbed system, which is the 0th term. Next we will order lambda times En1 plus lambda square times En of order 2, like this. We will expand the En like this. Next also we will expand the eigen function also for this equation with different orders of lambda. Lambda is the parameter and lambda is small here for weak perturbation. So first term will be 0th order term, n0 plus lambda times n1 plus lambda squared times n2, like this. So this is actually Maclaurin series or Taylor series, you can call it. So En1 will explicitly will be just Enk, let's say in general, so 1 upon k factorial del k of En divided by del lambda k at lambda equal to 0. This is the general expression. Now just put the value of En or n and n in this equation here. So h equal to En times n. So here h will be equal to h0 plus lambda v, n will be equal to n0 plus lambda n1 up to first order. Let's just retain the term up to first order. Then En here also will be En0 plus lambda En1 multiplied by n will be just N0 plus lambda times N1, right? Now you can break this term. You can break this term like H0 N0 plus H0 lambda times N1 plus lambda times V times N0 plus plus 1 lambda squared term. So we ignore the lambda squared term here because we are just retaining up to the first order here, which will be then equal to En0 N0 plus En0 lambda times N1 plus lambda times En1 N0 here. So now let's just compare the different orders of lambda here. Now this is the term of lambda power 0, means there is no lambda here. So let's just compare this term with different orders of lambda. So lambda power 0 term, which is H0 N0 equal to En0 N0, right? So this is the known equation we know. This is the time independent Schrodinger equation for the unperturbed system. Now let's compare the lambda power 1 term, which is H0, this term, this term, and this term, and this term, which is H0 N1 plus V times N0 equal to En0 N1 plus n1 n0. Now this is the expression we'll get. Now just you can just multiply with this bra of n0 term. You can multiply with this equation with this term here. So let's just put this ones n0 80 n1 plus n0 v n0 equal to en0 is the constant term, right? So you can just keep it outside. Then n0 n1 plus en1 is also constant, is the energy value just. So n0 n0, this equation will get. Now if we operate 80 on n0, if we operate this 8 0 with n0, then we'll like this we'll get en0. So we'll get en0 n0 n1 plus it will be n0 v n0 equal to just en0 n0 n1 plus en1 n0 n0. Okay, now just look at this. en0, this term is common here both sides, so we can cancel this term. Now we know that the n0 is the eigenfunctions corresponding to the unperturbed system, right? So these eigenfunctions are orthonormalized. That means they are orthogonal to each other and they are normalized. That means n0 n0 will be equal to 1. That means they are normalized. So this term will be equal to 1. So en1, that means en will be equal to n0 v n0. This is the expression we want to get, because en1 is the first order correction due to perturbation. Why first order? Because this is first order correction, na? Lambda power 1. So this is first order correction due to perturbation, which is the n0, that means the expectation value of perturbation term with respect to the unperturbed eigenfunction, zeroth order unperturbed eigenfunction, right? So is it okay up to this? Yes. Okay. So here in this question we know the perturbed term, that means here v is 1/6 gamma x cube, right? And psi 0 x, which is the n0 in this case, we this expression is also given. Let's say just ignore the coefficients here, all the constant term. So just let's say psi 0 is e to the power minus alpha x square, and the perturbation term is x cube here. So let's just compute en1. This is the first order correction. So en1, that means this Dirac bracket notation means integration of psi 0 star x multiplied v, then psi 0 x dx minus infinity to infinity. So minus infinity to infinity, psi 0 x is e to the power minus alpha x square, ignoring the constant, all the constant terms. V is the perturbation term, here v is x cube, it is in the question it is given. Now psi 0 x is also alpha x square dx. Now just look at this integration. this is a positive term, right? If you change x to minus x, this term will not change the sign, right? So this is a positive term. This is also a positive term, because if we change x to minus x, then it will remain e to the power minus alpha x square. So this, the sign of this expression will not change. This is also a positive term. Now x cube, if you change x to minus x, then the x cube will change to, if you change x to minus x, then x cube will change to minus x cube, right? Now when you are integrating minus infinity to infinity, that means from 0, x equal to 0 to infinity, there will be a 1 value corresponding to this integration. Now from minus infinity to 0, that means when x is negative, all the expression will be same, just the sign will be negative, right? So that means the total contribution to the integration, like from minus infinity to infinity, the total contribution will be 0. So the integration value will be 0. Why? Because this is positive term, this is also positive term, this is positive term, this is positive term, and this is negative term. So that's why from minus infinity to infinity, the overall contribution, overall sum will be equal to 0. So the first order correction, due to perturbation, which is en1, is 0. So there will be no first order correction here for this kind of problem. So the total for this problem, actually for total ground state energy will be total ground state energy. What will be the ground state energy? So our Hamiltonian will be just H equal to H naught plus lambda times plus V, right? So the total ground state energy corresponding to this H will be ground state energy corresponding to the H naught, which is H naught is harmonic oscillator. We know the ground state energy of the harmonic oscillator, right? We know the eigenvalue of the harmonic oscillator problem, which is n plus half times h bar omega, or n equal to 0 ground state. For ground state it is half h bar omega, and the first order correction due to V or perturbation term is 0 in this case. So the in first order, up to first order, the total ground state energy will be half h bar omega plus 0. So will be half h bar omega. Now we know the omega equal to root over of k divided mu, right? I think, yeah, root over of k divided of a mu. Omega is the angular frequency, k is the force constant, and mu is the reduced mass. So we know the omega equal to root over of k divided by mu. So it is half h bar root over of k divided by mu. So the total ground state energy for the enharmonic oscillator up to first order of perturbation will be half of h bar k divided by mu. So this is the option A. So option A is the right answer for this question number 34. Up only the first order correction. So first order correction is 0 in this case. So the total ground state energy will be just the ground state energy corresponding to the harmonic oscillator, which is half h bar omega. Omega equal to root over k by mu. So the option A is the correct answer. Any doubts? Okay. Okay, so let's just move to the next question, which is question number 49. Okay, so this is question number 49 from the same year. So this is the absorption maxima of two dyes X and Y are given 520 and the 460 nanometer, and the absorption data of these dyes measured in the 1 centimeter path length are given in the table. We have to find out the concentration of Y in the mixture in millimolar. So we know the absorption relationship here. So A equal to epsilon Cl, which is the A is the absorption, absorbance. Epsilon is the molar extension coefficient, and C is the concentration of our solution, or here millimole per liter, let's say, and L is the path length of light traveled. So we have to just apply this equation in this table here. Like for dye solution X, the concentration is 9 millimolar, and the absorbance at 460 is 0.144 and 520 is like this. So let's say for 460, let's say this is 1, and the 520, let's say it is 2. So for X absorption value is given, so 0.144 equal to just epsilon 1x, means molar extension coefficient corresponding to the dye X and at absorption 460 nanometer. So times concentration is 9 millimolar, times L equal to 1. So then again for 520 nanometer, the absorbance is 0.765 equal to, let's say, epsilon 2x. That means the molar extension coefficient corresponding to dye X, and lambda equal to 520 nanometer. So times concentration equal to 9, path length equal to 1. Like this, if we can construct another equation for the Y solution, Y dye, 0.912 equal to epsilon 1y times 12 times 1, then 0.168 equal to epsilon 2y times 12 times 1. Now for the mixture of X and Y, that means absorbance is 0.700. For 460 nanometer, mixture will be just epsilon 1x times, let's say, Cx times 1, path length equal to 1, I am not writing this again and again, plus then epsilon 1y, concentration is Cy, let's say. Now again for 680, absorbance equal to 680 at 520 nanometer. For the mixture will be epsilon 1y times, epsilon 2x times Cx plus epsilon 2y times Cy. Now from these two equations, this equation and this equation, or this equation or this equation, we can get the value of epsilon 1x, epsilon 2x, epsilon 1y, epsilon 2y, right? So if we can just get the value of all these four quantities, 4 epsilons, and put these values here. So we can just we know all these values here, so we can put all these values, and so we will get a relationship between the, let's say, this is, let's say this is A, the value of epsilon 1x is A, which A will be A will be just 0.144 divided by 9, like this, and value of epsilon 1y, let's say B, so B will be 0.912 from this equation, 912 divided by 12, like this. Let's say this is C and this is D. So C also will be 2x, means this equation 0.765 divided by 9, and D also will be 0.168 divided by 12. So we'll get a relationship between the A Cx plus B Cy equal to 0.700, then C Cx plus D Cy equal to 0.680, right? This is equation 1, this is equation 2. We can just multiply by C here and multiplied by A here, like A C Cx plus B C Cy equal to 0.700 C, then A C Cx plus A D Cy equal to 0.680 times A. We can just subtract these two equations, so this will cancel, and we get a relationship between the Cy times BC minus AD equal to 0.700 C minus 0.680 A, right? So Cy will be 0.700 C minus 0.680 A divided by BC minus AD. So all the values are known here. We know all the values A, B, C, D. So we can get the value of Cy, which is the concentration of Y in the mixture. So if you just put all these values and compute, you will get 7.7966. Now up to 2 decimal places, so it will be like 7.80. So up to 2 decimal places, the concentration of Y in the mixture is like 7.80 millimolar. So all clear? Any doubts from this question?
Yes, sir.
Okay, okay, then we'll meet next week, I think. If you have any doubts regarding these C questions, you can ask, or otherwise we'll meet next week. Okay, thanks Aziz, thanks for joining. Okay, then if everything is clear, so I'm just signing off, then we'll meet next week. Okay. Okay, thanks for joining. I'm just leaving this meeting. Okay, bye.